student. Today I am here about topic called coordination chemistry. I'm Dr. Sudas Associate. And you know, for the inorganic chemist, this chapter is very much important. For this, you have lots of book reference, bachelor level for different BTech courses and bachelor degree program course. So this is an important stuff topic. And so before we starting, we have to know background of it from Dalton 1900 years before 1900 18th century. There is Dalton to all the scientists. They have given the idea about the one electron neutron. Thereafter, have a compound. How you can explanation compound, how they are made, what are their existence, etc. Then we have found chapter is to be done. For this, any bonding with the metal and with the in the transition metals have found that there are lots of theory. First one, Warner theory. Next is next bond theory. Then crystal and molecular. So these five structure are given us a detailed idea about the bonding of transition metal. As what is the consequence? Consequence is the high spin, low spin count, electrochemical series. Next is crystal field stabilization energy, Yan-Teller distortion, and also spinel. So these are the consequences from this theory. We have an idea of this, how we can get the high spin, what is the spectrochemical that is spectra of the completion, what is Yan-Teller. So in this regard, a Nobel awardee, Werner, Alfred Werner, was a very top quality explanation done in the coordination theory at the age of 6 from of Zurich, Switzerland. He said that addition of 6 mole of ammonia to salt chloride in aqueous solution, and he gave done two tests. One is conductivity test is with silver nitrate. Have done a precipitation, and with this a conductivity study have been done with the help of conductor, and beautiful explanation have been about what is this. And if you go to this slide in platform where 1 mole of an bulk tetrachloride and 6 ammonia have been taken, and we have got yellow precipitate, yellow color. And if I take excess silver nitrate, and you know silver chloride is a precipitate, white precipitate coming out with the reaction with chloride and silver, and 3 mole of silver chloride have been precipitated from this solid. Next, we have taken same called 1 mole of cobalt carbonate, cobalt chloride, and 5 of ammonia. A color is purple, and it gives mole of silver. Next, we have taken copper chloride and 4 mole of this, got only one. Next, copper chloride violet color, we got only, so two different color, only 1 mole of silver nitrate. This is the observation by the conductivity, and how we can explain it, not predict. Warner help us figured, who have said that he proposed that, or postulates that, number one, the in coordination found metals or two types of linkage, valence, primary valence or primary valency, and two primary valencies are the normally ionizable side by negative ions. Primary valency is the normalized state value. Next is secondary valencies are non-ionizable. They are satisfied by neutral molecules or negative ions. And the secondary valency is equal to the coordination number fixed. And fourth postulate he have given us that the ions and groups found to the linkage the metal have characteristic spatial arrangement corresponding to current and coordination. So what are the postulates gives us that they have explained us a scenario of the previous experiment conducted by Werner, and from this theory easily postulate what are the effect is coordination type of action. So you can find when we take this ammonia, examine the four ions, because chloride, three chloride, one cobalt ammonia. Four ions we can, when it is taken three, five ammonia, have taken three ions. When you have cobalt, say, five NH2, four ions, but it is two ions. So we can explain that hexa for the secondary valency with the cobalt, one ion, and rest chloride at the primary valency are ionized, and it gives us the next is the secondary valency is the number of ions molecules that are coordinated to the metal ion. Werner assumed that secondary valency of the transition metals in this cobalt 3 complex is 6. The formula of this complex can be therefore written like this, and structure ionized primary valency, very constant, it is tightly bound, not ionizable easily. Total 3 plus 1, this is 4. 4 is coming from 3 plus 1, that is orange, and 3 given here, so it is red color. 3. Next is when you have taken chloride purple color, one chloride is inside the as a second valency, then we can got 2 plus 1, that is 3. Next is when 2 chloride is inside the coordination, 1 plus 1. So how we can get it is how it is 4 can also be explained like this, amount 5 plus 1. 3 plus 1, 4. This is the 4. So these are the explanation of the what we have got from Warner, simply matching with the fact. So it is a nice interpretation, and this primary and secondary balancing gives us details of the thing. It is a type, it is, and for this he got Nobel Prize in 1930. He is the probably the first inorganic chemist to get the Nobel Prize. An example of the metal complex is that the metal central nerve is a Lewis base. As we know in our acid base concept from the our books, yeah, T-Sarkar, it may other kind of books. Any acid which can take up one pair of electron is Lewis acid. Any compound who gives us low pair of electron is the Lewis base. So metal ions with the central is the Lewis acid base. So metal with the H2O ligand as the metal scenario, and got this example like this structure, Lewis acid and Lewis base, and how strong are the bond we can get, that is the truth which is ink, uh, Fe4 Fe6 X go can be used for certain heavy poisons. So this Prussian blue made a complex bond, and when you have this 3CN, modest toxicity can be metabolized to produce a CN which is very toxic. And when we have KCN is poison by itself, the normal valence, the Werner complex, the primary and secondary valence there. Next, the color. Cobalt amine Cl3 and cobalt pentamine Cl2. These are two complexes. When they react differently, the silver is that it gives us silver chloride, 3 silver chloride. It gives silver chloride is the complexes. The color and how we perceived it, it can found the color, black color coming out. We know as it known that all the color coming in black because all are absorbed. When it is not absorbed, then all are evolved by from this product, our white. Okay. So we can found that color black and white coming out, we know, known to us. Next is absorption and reflection. If the sample absorb all at the orange, sample appears orange. So all the all the color coming here from the compounds, and it is all about orange, then it is color is orange. And when all are reflecting, we get a green perceived color is white, like this one green color is the. And what are the different types of coordination? We found that AX2 0, the complex, that a bond angle of 180, and these are the beryllium, all this geometry. And when AX2 1, it is bent one 120 degree of bond angle, that it is is bent style minus when it is AX2E2 then bent 109 degree 5 minute is like this and H2O OF2 that the AX2E3 linear 180 degree well that it is F2X when is AX3O0 diagonal by 120 degree that this is the and EF3 P003 is the example right. Next is diagonal bipyramid. It L5 structure diagonal bipyramid that the different types of complexes present in the bird nature. Next is capped. Capped is structure, tetrahedral structure. The example, horse structure. The example, the square planar is very important angle. Then XC4 diagonal bipyramid. The three angles P L5 square pyramidal example. Diagonal planar. It is the example. Octahedral. So very good number of octahedral curve present in the nature. We can found it. Next is pentagonal bipyramidal. This is the structure. Pentagonal bipyramidal. This is the structure. The pyramidal. It is a bipyramid. Next is square antiprism. The example. Then there is T-capped diagonal capped square capped square antiprism structure. It is anium. There are lots of examples we have given. So there are coordination compound is given a variety of compounds. Current angle go to the power variety. Then we go to the ligand. What are ligand? Ligands are especially species that is neutral or anionic bonded to the central metal. They can be attached to the metal center through a single atom or two or three atom or higher that is bidented. Such pentadented or bidented or higher ligands are called chelating ligands. What are the ligands? Pentadented and higher pentadented, polydented, bidented or higher called chelating ligands. The name is ligands. These are the common used ligand: aqua, in, in carbonyl, chloro, bromo, hydroxycyano. Next is some chelating ligands are there: chalato, diamine. Next, for your self study, you can go to the your book. You can find the structural isomer. That the example structural geometrical isomer, optical isomer, and structural ionization, hydration. You can book. Next is variation of oxidation state. It is found that scandium plus 3 and titanium 1 to 4. Like this manganese you can find here 1 to 7 oxidation state because manganese has 5 metal, 5 elements, 5 and from S got electrons plus 7 electrons. So increase of number of oxidation manganese and all are possible only in the very important postulate from this. Next is decrease in the number from zinc due to the pairing of p orbitals due to the pairing all the electron at stability of the higher oxidation is along scandium. Manganese are more powerful oxidizing agent. 4, 7 and iron 6. 18 electron rule are there given by Sidgwick, and they found that metal per electron lone pair ligand gives us one electron. 18 1, 18 electron is there, then it is stable. For example, nickel tetra carbon right, S2, then it is plus 4, 10 plus 4, 18, also 18. So 18 electron explained by molecular orbital theory, filling all the molecular and none of them. So EAN use and limitation. Effective nuclear atomic number of the some metals in confined, it is atomic number 4. They are like this, number of ion 6, there the EAN. And valence bond assumption and failure, ligands from covalent coordinate bond to metal or assumption. Next is ligands must have lone pair of electrons available of empty vital for energy, metal bonding, and atomic hybrid orbital used for thing rather than can explain shape and stability of the metal complex. So this is the valence bond theory. Uh, shapes. What is the this kind called plus 3, 6, and this the high spin. Okay, this is the depression, the diamagnetic. Low spin diamagnetic. Cobalt can be type sp and sp. This given. Thank you and for watching this coordination topic. I am very excited to come my organic topic, important topic. If you have any query, net and ID 36 at yahoo.com. I'll be delighted if you have any query easily explanation or very clarification, or if you have any data needed, have any other for this normal references, all the if you go to the all the books, bachelor level piece or JD Lee, lots of books are there, bachelor level. Current, thanks a lot. And